philosophers of physics started looking at kind of in late 1970s. And kind of theoretical context for all of this is the geometry I'm interested in is classical GR, classical general relativity, understood in a very minimal way. Okay, so we're not trying to solve any interesting equations. We're not going to any interesting observations. We're only looking at smooth and dimensional connected Hausdorff variance and manifolds. So that's a sort of theoretical setup. And yeah, this is sort of the plan for this talk. I will first kind of like quickly summarize what we know about observational indistinguishability and observational indistinguishable spacetimes. I'll first do it in a kind of like more accessible way before going into temporal notation. And then I will ask, or we will ask, or we will collectively. I think there's some things that we know that kind of people investigated and gave good answers to, but I think there's a lot of unresolved questions. I think one could ask about whether the definitions that I will take you through in just a moment kind of exhaust the logical space of possibilities, or there are other alternative notions of what it may mean for spacetimes to be kind of from the point of view of observers inside the same and kind of, but nevertheless kind of globally different. I will ask that what are the examples? Can you come up with other examples than the ones that were sort of discussed in the literature so far, so to speak? And then I will ask a question: how to live with all of this zoo of horrible examples? And you should not worry. If the answer will be that mostly you have to live just as you did so far. Okay, so this is kind of like the motivation for this whole kind of little enterprise in the study of Lorentzian geometry. So consider some spacetime FG, right? Maybe this is Minkowski spacetime. I'm sorry, I mean US Minkowski spacetime. Or maybe this is our kind of whatever small perturbations of the FLRW spacetime happens to describe the observable part of the universe.
Yeah, all good.
Okay. Or maybe this is for other complicated space than you think we might be living in, right? Now we will say that some other spacetime, NH, is an observation indistinguishable counterpart of my original spacetime. If no observations made anywhere inside of M, you tell of M and N apart. All right. So you're thinking, oh, maybe this is the spacetime I have some good reasons to think is my universe. And we're asking the question, for this universe, could we find some other universe that no matter where and when and how you make your observations, no matter where we are located, no matter how deeply into the past we look at, could we be in a situation where those observations cannot distinguish whether we were here or we're there? Okay.
So would you distinguish between, say, a black hole space-time and a boosted black hole space-time? They're different models, of course.
Right. So I have this assumption that I will assume that this NH is not isometric to MG. And if I think of boost as kind of like a dynamical symmetry that distinguishes between these two spaces, then I would not think of them as, so if I think of this as kind of like just descriptions of a symmetry, then I would say, I guess I would tend to say that these two are isometric.
So are you saying a black hole and a boosted black hole are observationally indistinguishable or no?
I'm not sure. I think I don't view on this. I guess I would need to know more about what exactly you mean by boosted black hole.
What would you write down two geometries?
Okay, yeah. Then if they're not isometric, then
well,
But presumably,
They are isometric, of course.
okay, yeah. If they're, the way I think about this, if the two spaces are globally isometric, then I think of them as one and the same space time.
So,
It
so
kind of
momentum,
doesn't matter whether, I boosted myself in Minkowski space time, I'm still in Minkowski space time.
Minkowski space. So you would say momentum is not observable
Oh.
because these two spacetimes, and they have different energy and momentum, right?
Mhm. Right. So,
But they're isometric.
well, isometry should preserve physical properties.
No,
I think.
no.
Yeah.
Different work. I mean,
It might help, it might help Juliusz to introduce the formal definition of
So
observation,
the only difference between these two is a global difference in some sense.
because according to the official definition, they are
The global
observations.
difference, then, there's this part, I said no observations, and this is a very vague notion. And I will make it precise, kind of here. So I think if you're working, if I think of myself as located on an extendable curve that goes all the way to null infinity, then I guess I could distinguish between them, right? Because the mass or something like that, I could measure at I plus, right? In the boosted black hole space time, the mass of momentum or something like this. But I guess if I'm kind of observer located at the point inside of this, I don't think of myself as living arbitrarily long. Then I guess I would say if I'm thinking of this, it's like I'm not sure I'll define this impressively, but I would think that the observation is distinguishable point-wise, but not necessarily along the inextendable curves.
it seems like a
Because there will be
question
some-
with a yes or no answer. Are these two spacetimes equivalent under your definition or not? You didn't say a space-time endowed with some observer. You just said you
Right.
were
Yeah, I just
you're
took a
characterizing
Lorentzian
equivalent
geometry,
classes of space-times.
right, by the isometry relationship, and so I guess that that means they're isometric. I have to think of them as observationally as identical, not only from the point of view of observers side of the space-times, but equivalent, totally globally. Yeah, I guess that comes into it. Yeah.
There's a much more subtle version of this equivalence.
Where I guess I would not only have to assume that I should think of isometry, but also preservation of something else. For physical identification of the manifold, the Lorentzian geometries.
Eric has some comments in the chat if you're interested.
Yeah, Eric is my co-author in this, so please cut me, Eric.
Eric says that according to the official precise definition, they are in fact observationally indistinguishable. For each point in one, there's a point in each other. So he says that they are in fact observationally indistinguishable. For each point in one, there is a point in the other such that the Pasnell cones and their interiors are isometric. So
Yeah,
I think that's.
but yeah, I guess.
This would not.
I guess this is our official answer. Yeah.
That's what I thought your official answer was. It's
Yeah.
not the conventional view in general relativity, right? Usually you would say momentum and energy are important observable
Yeah.
in space-time. But I mean, it's fine. It's a
but
free
in this-
world. You
in
could
this-
define it this way.
Right,
but-
yeah, so, but I guess it's
And
a
it's-
subtle thing because those are not local properties that I determine inside the global parameters of those.
Yeah,
functions.
But usually we would say most,
And
in general relativity, most of the observables are
Global.
global. So
yeah. But then okay, so then I think it kind of should depend who I think of myself as observer, right? Because where do I measure these observables? Like I measure them at Scribe Plus or other location kind of like this. So then if I think
I mean,
of
astronomers do it all the time. We just measure
Right.
the mass of M87,
yeah, sure.
So
We-
ask them what they're doing.
Right, yeah.
Tell them that's not observable.
I think what you guys are doing is you think of yourself as living at discrete class, and so then you think of observer as basically an extendable curve rather than a point. And so then in that sense, you look at the whole of that space-time rather than as kind of like sub portions of it. And that changes the epistemic situation, certainly the cognitive situation. And this is why I said I love giving talks at the PHI. I typically cannot make it a slide like 3. This is great. Yeah, so I said, observations made anywhere inside of MG can tell these two spacetimes apart, and that's not a very precise statement, right? Because you can ask me what are the observations and what are the observers.
Right.
And here, I guess, is this point where, according to this, if I think of myself as located at the point, then it's hard to make any distinction between the normal kind of like static thing and the boosted thing. But if I think of myself as, oh, I've seen all there is to it, I'm along an extendable curve, then I can make the difference. Because I'm located at a point where I can measure kind of like the global property of the whole history of that system. So sort of like the usual, I think idealizations are kind of like this rather than this. I guess does that make sense to you?
I mean, it makes sense. It's not, I mean, there is
I know it's a free
huge
country.
literature about this in general relativity, and it gets much more complicated in boosts. There's the
Of
whole
course, yeah.
BMS group, and it's not a solved problem.
Right.
But it would just, I just wanted to understand what you were saying.
Yeah. I hope this was helpful. Right. Yeah, so what are the observations about? Again, this is a highly idealized picture of observations because I will assume that we can access anything in our chronological or causal past whatsoever. And of course, this is not how the universe is like. It's very hard to access anything past, I guess, the recognition surface, more or less. But I will disregard it because this is global space and structure kind of talk. And yes, the next question is what are observers? And I'm actually glad we had this exchange because I will, at some point, like in just a moment, I will make distinction between the notion of observational indistinguishable that works along points and that notion that works along extendable curves. And those notions are different, and things can be observation indistinguishable. One thing could be observation indistinguishable from another in one sense, but not in the other sense. And so I think one of the kind of advantages of this is that it forces us to think more deeply about idealizations that we make, why do we make them, how do we make them, which examples to care about, and so on. And yeah, so I think a useful piece of terminology simply because it's efficient in terms of syllabs is this terminology that John Norton introduced. So instead of talking about something like an observationally indistinguishable spacetime in a given one, I'll just say a Nemesis spacetime. So the kind of way to think about this is, here I am, I think in a random spacetime, and someone comes and constructs a very globally different spacetime. This is my Nemesis, that spacetime, because I kind of can determine whether I'm in where I think I am or whether I'm kind of located in this more or less conspiratorial Nemesis spacetime. So the Nemesis one is always kind of like the problematic sort of contrived example, so to speak. Okay. And so now the question is, what do we know about these notions? And even kind of like as simple as they are, we do know quite a little bit. So first thing we do know is that there are kind of 3 standard definitions. So we say that a spacetime MG is weakly pointwise, observationally distinguishable, or like weak POI nemesis. If for any point in M, there is a point in the other one in N, such that their chronological paths are isometric. So any signal that's in the chronological path. So anything that is related to by a time-like curve is in the set. And we only require that for any point in here, there is a corresponding point in here, such that no matter where I am located in the original, I cannot distinguish produced space types. So I call it a weak relation because we do not require that here that the relationship is symmetric. It could be the case that once I'm in the Nemesis space, and I can tell whether I'm in the Nemesis or in the original, and according to the first definition, but not according to the second definition. In the second one, we want the relationship to be symmetric. So I cannot distinguish the original from the Nemesis, and also vice versa. And this is weak or strong depending on whether it's symmetric or not. So strong is symmetric, weak is not symmetric, and P stands for points. And the second good notion you could have is you could have something like not work along the points, but in extendable curves, and everything else remains as it was. So I'm looking at chronological passes of future inextendable, I guess time-like curves. I guess they could be arbitrary time-like curves, and looking at whether they chronological paths are isometric. And you will look at this and you will say, hey, look, but why there are 3 standard definitions? There should be 4 standard definitions. There should be something like a weak kind of inextendable curve, so like COI. There should be such a notion, and of course there is, but in the kind of like standard philosophy literature from 1970s, no one explored it, which I find a bit surprising. And actually, most of work on this topic only works with this notion. So the kind of stronger symmetric notion, and this notion is almost entirely disregarded. People don't prove theorems about this. People don't think about these alternative notions that much. And so yeah, in particular, this weak version of this has not been explored yet, but I will say some things about it. And I should also note that definitions are usually stated in terms of this chronological precedence relation. You could think of also kind of like taking the closure of this. And when I asked people about this, they told me to meditate and see that nothing changes. I haven't meditated hard enough, but I think one could also consider this relationship and see if anything changes. But we won't do this today. Okay. So now there's a kind of like a standard construction when people think about these questions. Standard construction of the Nemesis spacetime. And I will kind of like briefly describe it in the words, but they all have some pictures, and maybe they will be helpful, maybe not. But if not, I guess good recommendation is look at this paper and meditate about it. But it's a good solid construction. It works. So basically, what you're doing is you take your spacetime, assuming it satisfies a very mild causality condition. It's not such that all of the spacetime can be seen from a single point. None of these are. And assuming it's a Hausdorff, you can cover it with a countable set of points, such that any point in spacetime whatsoever be contained in the chronological path of this countable collection. And then what you will be doing is you will kind of like duplicate the original spacetime, excise some regions from it, and glue those regions together. And so it's sort of like you take multiple copies of this spacetime, spread them like kind of close to dry, so to speak, and then glue them together in various ways. And so what happens then is that you obtain a spacetime that kind of by construction will be the same from the point of view of every kind of observer confined to the original, because we sort of like only used elements of the original spacetime in constructing the Nemesis spacetime. But they can be globally very different because we'll have a lot of freedom, sort of cutting and pasting and including additional regions and what further do with these sorts of objects. Yeah, so this is sort of like the description, but maybe in the interest of time, I'll just show you the picture. Here's how it starts. You take this you have kind of like, oh, I should say this is from, the construction is here, but the pictures I stole from this paper, they're not mine. So basically what happens is you take, with the original space name SMG, you take infinite number of copies of it, countable, and in each of them, you take kind of slices, sorry, space-like slices like this, excise them, so remove them, and then you will be kind of gluing lower edges of those slices to upper edges of slices in the other copies of the space. And so in this way, this is kind of like a closed line sort of thing, right? You take first thing, excise some of it, hang it to the next one, to which you excise something else, and then sort of, well, this, we don't typically do this to flows, of course, but we can kind of stitch them together. And this is kind of how stitching works. Like we take the upper edge of this region and stitch it over here to the lower edge of this region, and the upper edge of this one we stitch to the lower edge of this one, and we sort of like continue in this way for every other copy of it. So this is what I will denote as the standard construction. In the stone.
Is this really indistinguishable?
It is.
Because my past code will start going through those cuts.
Okay, this is why it's weakly pointwise indistinguishable from the original one. I think this is, yeah, this is a very important thing to stress. You can see that this will be weakly. So if this is the original I started with, right? Here I'm kind of like going farther and farther up with those points P1, P2, P and so on. And so the chronological past of that will look the same no matter where I am. Well, causal past actually also, right? But there will be a lot of points in the Nemesis spacetime that cannot be isometrically mapped to the original, take any one above one of those slits K. And of course, also this will not work along future inextendable time-like curves. But interestingly, people in the 70s explored those situations on inextendable time-like curves, and you have the steeper space-time, then you can sort of do kind of analogous construction, but it's kind of highly specific. Okay, yeah, so some facts. What do we know about these things? First is that if under in a sense, there's always if the original is not too crazy, it's not totally bizarre, I cannot see the whole original from a single point, then there always exists a weak POI nemesis, so asymmetrically along points, which has the same local properties. And you can sort of see this from the construction, right? Because the local property is something that falls in like the neighborhood of a point, then I basically constructed this from elements of the original only, so those local properties will be preserved.
So it's just a question of definition. So when you talk about weak, right, weak POI,
Yeah,
you are saying for a given selected point, or is it for all points in the origin?
it's for arbitrary point from the original.
Okay, then I'm a little confused about your
Stitching.
stitching, because I can always choose a point for which the stitch is in the past, and then it will not be
Okay,
indistinguishable.
so so here's my original spacetime, right? It's this with no point removed, whatsoever. I cover it with a countable set of points, chosen anywhere whatsoever. And now I'm treating in I take for any of those points, P1 somewhere here, P2, but P2 could be higher up here, P3 higher up, and so on. I'm taking 2 copies for each of those points, so to speak. And now, so here's my original. Let me just take like a sequence of points here, 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 and so on, going higher up. And so here I have kind of like this copy that's kind of like yeah, I might have to shift some of them, but I think this is chosen so that it's outside of P1, so it's good. So it's sort of like, for the first element of the sequence, I will have its chronological path over here. And I make no changes to the path of it, so it's okay. And for the second one, I'm doing the same, but in another copy, that I can include the copy of the first one. So it's also okay for the second one. And I continue like this, because I will have kind of like M2 over M2 over here, and 3 and 4 and so on. Oh, sorry. And 1, 2. How does it go? Yeah, anyway, I will have a sequence.
No, I got it. I
like
completely missed. Okay,
Yeah.
thanks.
Yeah. No, thank you. That's a great question, because this construction is confusing, and it's sometimes not immediate to see that we can truly find anything, any appropriate counterparts from the point from the original. Yes, so under some notion of a local property, it turns out that this is also a subtle question, but I won't torment you with this. But there's so many definitions of local properties you can write. It's amazing. There always exists that if the original is not too bizarre, then there exists a weak POI nemesis with the same local properties. And moreover, we can prove that. I shouldn't say we. I guess Eric can say that it's collectively we, but I don't have this. No, okay, I'm kidding. It's not hard. One can prove that if space-time is isotropic, globally hyperbolic, and has some other kind of as large as it could be properties, then we can construct a nemesis that has none of those properties. And so the way that people typically interpret these constructions is, okay, here I am in my FLRW model, and my observations are confined to only to like a finite portion of it. Do I have a justification to say that my whole universe is also FLRW? And these sorts of examples can be used to argue that, well, no, I cannot extrapolate outside of the confines of the Hubble volume I have access to, and I can construct actually a number of statements of observation the same, no matter where I am in the original. So it's kind of like classified with some Copernican principle, and yet they can have very different global structure. And so in a way, if I think of myself as kind of an observer located at the point, then there's very little I can know about global structure of space-time. This is kind of like one way of interpreting these examples. In this sort of like the context in which they were originally applies. And you could argue also that in a way they show that prediction in GR is a very hard enterprise, because if you think of prediction as something that I make on the basis of data that are confined to a Cauchy hypersurface, then unless I'm in a space-time which is spatially compact, then the Cauchy hypersurface is never in my causal path, of course. But if it's not in my causal path, then I can use this construction basically to locate those slits. Sort of, if this is partial Cauchy I have access to, then I can use this sort of construction to locate kind of like the incised point or a hole or something like that on the very edge of the domain of dependence of this partial Cauchy hypersurface. And so you can say, oh, I'm making a prediction that something will happen at this point over here. Then someone can kind of map with the nemesis the original space-time, where actually I cannot determine what happens at that point, unless the point is exactly on the boundary of the domain of dependence of the hypersurface. And Martin Research, who you know very well, better than I do, isolates some conditions under which weakly POI spacetimes can actually be isometric. So in some cases, this whole thing can be sort of like limited in a way. But those seem to be highly special cases, and they don't quite give us what we want to. Okay, so yeah, this is the intro to this whole thing. I will ask 3 questions now, and we're having questions during, so maybe it's okay. Please bear with me. So I think the first question is: are there any other definitions than the 3 or 4 that I showed you? Right? You may think, oh, is this all there is? Like maybe sometimes I can make observations not at a point, but also not at a kind of a whole feature in extendable curve, right? There could be other notions, or maybe I can have some wiggle room. And I will ask a question: do we have any other examples? I just showed you this kind of like highly contract closed flight construction. Can you come up with other examples of Nemesis spacetimes? And if I come up, like I'll bring the bag of Nemesis spacetimes. It's kind of like I'm bringing a bunch of these animals over here. How do we live with them? So those are kind of, so in other words, this is a question about what to think about this, how to interpret this. Like in this cosmological case, this seems to make some kind of like skeptical point. We can know very little about global structure for spacetime. Should we make this point in those other examples, or maybe we don't have to worry about this point in those other examples? Maybe this sort of investigation is good, not just for making skeptical points, but also for just understanding theory or something else. So I should state here, because it's being recorded, I'm not making claims that like black holes do not exist, we cannot detect them or anything like this. I don't think you can make, we don't think you can make these claims on the basis of Nemesis spacetimes. However, I will show you a bunch of Nemesis spacetimes to black hole spacetimes, which is why I wanted to say this caveat first.
So I have a question for you.
Of course.
On your COI statement, strong COI statement, you're looking at a set of, you're looking at all possible time like inextendable curves.
Or points.
And they're pretty fast linear dependence.
Mhm.
Now, if you take a convention, you could imagine that you could forget the quotient of rest with all of these guys.
Right.
So where would you put your slits such that you would miss them when you do a, is that
Good. So
but you're looking at the domain differences for at all points.
good. So this is why I said this is a POI Nemesis. So you work along
Okay,
points.
yes, yes.
It's much harder to construct a COI, but if you have kind of a cosmological horizons,
Yes.
then you can do this, right? Because you can imagine like taking different copies and kind of like reordering them.
So when you
appropriately.
say full free, you mean more horizons also, or
Sorry.
when you say full free?
Oh, I
you-
just quoted from that paper. What they mean by whole free is that kind of like domains of dependence are as large as they could be, something like that. But it's a subtle notion that I don't want to get into because I introduced too many already. Yeah. Yeah, but it's in general, it's so much harder to construct something like a COI nemesis, and like a strong COI nemesis is really hard to get. And a weak POI nemesis is very easy to get. And those in between, well, let's see. Oh, I have this question about other definitions. I think I will skip it because I mean, I'm more interested in the other examples. I think you're also more interested in other examples. But basically, it's very hard to come up with other definitions. We do have one, which has sort of like, we do have one, and that improves situation of prediction and asks me over coffee or during Q&A. So the upshot of this is it's hard to come up with other definitions. We only came up with one candidate, and we think it's not a bad one, but yeah. Ask me later. I think the more interesting part is this. Can we come up with other examples of nemesis spacetimes? Because we only have this one construction, right? And you may think, oh, so much cutting and pasting. I don't like this. Well, I think there are some examples. So here are some that we were able to find. The first one is, it's a really weird one. So in this paper, Harada and their collaborators, and they do sort of classification of the causal structure of FLRW spacetimes, which is linear equation of state. And they also allow for, like, it's a very kind of wide classification. They allow for negative pressure. So like, there's a lot of weird things happening there. And among those spacetimes, apparently they found one which is like Minkowski spacetime that's glued to the FLRW solution. It sort of like erupts into FLRW. And so this is an example of the Nemesis spacetime, right? Juliusz. Depending on sort of your notion of Nemesis spacetime. It's a pointwise Nemesis, weak pointwise Nemesis, the original one. Of course, if you're here in the kind of like model that erupted into a cosmological one, you can very easily distinguish this one from Minkowski. But if I'm at a point like Minkowski, even if I'm for some class of curves, I'm like a Rindler kind of observer, then I may never hit the surface at which this space-time erupts into my calculation. So sort of like the causal structure is kind of like this, the Minkowski part, and this is the Minkowski part. And so then, of course, if you're kind of like a Rindler kind of observer, then you may never cross this transition surface. Okay, so this is.
You just might need to use a darker marker in the
Oh,
future
marker.
for people to see.
I want to use the. Can I use this one? Like in the arrays? How do you do arrays? Oh, next one. Yeah, so the example is sort of like this. And if I'm a Rindler observer, then it's hard to distinguish this. And of course, also at any point. But once I'm over here, I can very easily distinguish where I am. So this is only a weak Nemesis pointwise. It's not a full COI Nemesis. It's only for some kind of observer. It's in this space time. Okay, so that's cool. That's one new example, right? Here's another one. So Hans Ringström in 2013 wrote an amazing book on the cosmology and stability of our universe. And what he does is he uses the partial differential equations machinery for group existence and well-posedness of the initial value problem for Einstein class of matter system. And he considers cosmological models which are initially expanding, a positive cosmological constant, have a bunch of other nice properties. And then he shows that at some distance from the Big Bang in those models, practically any spatial topology of the space-like section is allowed by the observations that we make kind of like sufficiently far away from the Big Bang. So, and of course, if you go kind of like farther up, then you cannot also tell, right? Because we have cosmological constant that kind of makes our epistemic situation even worse if you look at cosmological horizons. So I think this is very remarkable because this shows that a form of observational indistinguishability is not only limited to this cut and paste kind of constructions, but it can be shown with other means and it can arise dynamically. So in a way, some of these problems cannot be solved by saying, oh, Juliusz, you did all of this cutting and pasting on my favorite spacetime, don't do this. No, we can also have things like that dynamically, or at least seems to be so. And moreover, you could think, you know, I made a bunch of these holes, maybe if I had in the construction, right? Maybe if I had some kind of a condition that forbids holes in spacetime, I could say, let's disregard them on the grounds of having a hole and only look at kind of hole-free Nemesis spacetimes. But here a number of global properties can be shared between these spacetimes. And so it's not so easy to kind of rule out Nemesis by positing some additional conditions. Okay, and now I want to take you through like, can I still take you through like 5 black hole Nemesis spacetimes? or do you want me to wrap up very quickly? Let me take you to some of them. Okay, so the first two will be kind of what you do is so in all of this, I will be kind of thinking of a black hole spacetime as just regions 1 plus 2 of Schwarzschild. I think the argument can sometimes be made more general, but not always. Okay, so I'm thinking in terms of this, right? Ignoring this part entirely, whatever is there, never mind. And also, I'm not putting like a collapse process on it. That will be important. Okay, so of course this is black hole spacetime, right? We have the tracking region, event horizon, in singularity side. think of ourselves as being here. And the first Nemesis space-time is you just run the construction that I showed you, all of this cutting and pasting over here. And so to do that, right, you have to pick a bunch of points that covers this whole thing. And you can pick some of them, like maybe the first one is here, second is on the inside, the third is on the outside, the fourth is again on the inside, right? You can kind of, we have complete freedom about how we pick them and we order them, right? But of course, this is fraction, so of course you also like a curvature gradient on this whole thing, right? And if you kind of pick them like this and kind of like alternate first element place reach the second and third and so on, and do this cut and paste construction, then the resulting Nemesis space-time does not have to satisfy any sensible Colloquium conditions. It won't have any kind of sensible asymptotic. It doesn't have to have any sensible asymptotic structure. And so if I think of a black hole space-time as defined by event horizon and that assumes some kind of asymptotic structure, then this Nemesis doesn't have to be a black hole space-time at all. So black hole space-time would have a Nemesis space-time that's not a black hole space-time. And this one can also be made geophysically complete, right? If you allow yourself arbitrarily strong violations of energy conditions. So a Nemesis for black hole space-time can be non-singular. Horrible.
I'm a little confused. What does the law of conditions have to do with the black hole, it being a black hole space-time?
Oh, if I think of black hole space-time as defined by event horizon, so this means I need to have some notion of spray.
Okay.
Yeah. And if I don't have like any kind of sensible convergence to an asymptotic solution, then I don't know what spray would be in this case.
Okay. So you don't know what the
Yeah, exactly what the right kind of like boundary for the light phase to evaluate would be. And so oh yes, I put this here. I said myself. So under some definitions of what a black hole is, it's not a black hole space-time. It could still have like there will be a lot of apparent horizons, for instance, right? So in that sense, it may be a black hole space-time, but in the sense of the kind of like Sprite plus space definition is it's hard to see what it's black hole space to be. So sort of depending on what you think the defining feature, it may or may not be a black hole space-time. I guess it's more question to say. Yeah, thanks for considering that. Okay, yeah. Now you can also do the same, but rather than do it kind of the whole thing, you can just do it to the inside, right? You can find over here to cut and paste thing and just glue it to the standard exterior region. And so then you have a Nemesis, the black hole space-time, which is also a black hole space-time. So there's all kinds of Nemesis space-times. It's fun, right? Here's the third kind of way of thinking about this. This is like a kind of like example that is sort of like cheating a little bit. That basically what you do is take t equal constant surface and to glue the whole future of it. This is an Nemesis space-time, maybe not very sensible because you say, oh, but it's so small, like I should extend it. But it's a separate discussion. But it's fun because it's a symmetric Nemesis space to be original, right? I can map from here to here and back, and yet this one doesn't have the notion of spray as well, and on the formality. So in a way it differs.
So I guess like out of curiosity, in the case of like say you have a Riddler observer and you had, let's say, a short shield black hole, and at least in the region like close to the horizon, a short shield black hole looks very much like Riddler space time. So if you just consider like this subset of this area, and you could say that, I guess you're saying that in that subset, the short shield and the Riddler space are nemesis to each other.
Yeah, I guess I would say that, yeah.
But the thing is that observers in each of those space-times see very different things, right?
Well, that depends which observers, right?
Yeah.
And at what points.
I mean, like, both them will see radiation and stuff, but the one is an apparent horizon. And are you saying that like they should not be able to distinguish a real horizon from an apparent horizon?
Oh, I don't want to, this is recorded, I don't want to make any statements.
Okay,
That's a good question, whether I could kind of like distinguish between various of those nemesis space and but something like radiation.
Yeah,
because
well,
this is what we're getting at, right?
yeah, cause like,
Yeah.
I guess what you're saying that these space times are observationally indistinguishable.
Right, in this kind of like Lorentzian sense, right? The causal path map isometrically.
Okay,
And so I think it's a good question whether there could be kind of additional effects that would help me in distinguishing whether I'm here or here. And I think it's a good question, but it's a subtle one. So if you for instance agree with people like Matt Wieser that working radiation is like a mathematical effect that only kind of like really needs some kind of an observer horizon, then I guess I would also get that in this one. But if I think it's a truly global effect that I will measure over here, then I guess it cannot distinguish. It's a hard question because also like those for the calculations that we do for like auto radiation effect and so on, we very often develop global structure assumptions
yeah,
that kind of guarantees you like existence in the uniqueness of state, right, and so on. And those properties, you just won't have them in some of those nemesis space times. So I'm not even sure whether I wouldn't be sure how to kind of try to argue that I could find wonder radiation in just space time of radiation or for it to be like a good background for a QFT, which I guess would be maybe a way of distinguishing from the original object. Yeah,
yeah, so I guess.
confusing.
I guess, so I'm understanding that, I guess like maybe I was misunderstanding. I guess, so I was sort of thinking like, oh, you could do a conducting experiment, but you're basically talking about points and their past. So like,
Right.
it's more of like if you're in a situation
Yes.
and you have the two, you make an observation in one space time, it looks exactly the same as another space time. There exists these two globally different space times that look the same, at least to the past of that observer.
Yeah.
So like,
Yeah.
it doesn't mean that you necessarily in the future that you couldn't do something.
Oh yeah, absolutely. Right. Yeah, sure.
Okay,
I can do things in the future, like in this cut and paste picture. Once I pass the slice that was just cut, I can
Yeah.
definitely
okay,
determine.
yeah,
That's the subtle difference between and strong notions, right?
yeah,
Yeah.
okay.
Yeah, I think it's a great question. Like it's a very hard question. How do things such as radiation so on, or like the standard QFT and background behave on expressed and with causal properties? And some things are known, but very little. Let's chat later because I have two more nemesis to show you. Okay, just two more. The first is I think you're familiar with this. It's like a regular black hole solution. So you take. You're saying, okay, maybe, maybe there are some kind of there's additional new physics that enters somewhere here on the inside. So this kind of part of the standard puzzle diagram inside of the black hole should be replaced with something, maybe with kind of an asymptotically de Sitter core, or maybe with an asymptotically Minkowski core. So if it's asymptotically Minkowski, then you end with a diagram kind of like there, kind of like this, right? And at least in this paper, essentially, these are claimed that they can push this energy condition violation physics into arbitrarily small region in the deep core. And so I think you see from this that if I'm an observer confined to the exterior, then it may be very hard to distinguish between the regular black hole solution and the standard one. Even if I think of myself, I'm assuming no quantum effects, and of course that's not sort of the point of those models, but with quantum effects I can distinguish what happens at the end of the evaporation. So that improves our epistemic situation, right? Which is good. But if I'm confined to the exterior, then I get a COI nemesis. And even a strong nemesis. Again, if I'm only looking at the exterior. But this is not even a weak POI nemesis. So can I get a weak POI nemesis? And the short answer is yes. If I kind of like do a mixed solution, I cannot write it down analytically. It's horrible. But basically what you do is solution that is partly standard singular function structure and partly this asymptotic whatever structure. And if you do it in such a way that kind of people who fall in early get practically the singularity, but then somehow you get this energy violation physics that saves those who jump in later, then you claim that this is weak POI nemesis to be original one. Whoa, okay, it was right? So how to live with all of this? So people typically take this, I think it's a common view that nemesis space-time establish a form of skepticism. I am here, but I could just as well be living here, and I just don't know, right? And there's sort of like a line of responses. Oh, we should ignore them. They're unphysical, but reasons are kind of like not always very clear. So I don't want to make skeptical claims. I think what like I and Eric and hopefully you also have learned from this is that even if I think of observations in just simple geometric terms in purely classical or ancient geometry, what we have learned is that we have more examples and more methods of constructing them, right? We have cosmological examples, and PD examples, we have all those weird nemesis examples. Some of them are constructed by cutting and pasting, but not all of them. So we have more examples, that's always good. And I think we also have kind of like a better understanding of how all of those notions, like strong and weak and points and curves, how they relate to each other. So it's kind of like a complex landscape. And I think like as a philosopher, my job is to kind of come and take on problematic notions and make them more complicated. And we have seen all of those examples of weak POI nemesis that are not strong, or like strong POI for some observations, and weak POI everywhere, but not strong POI, like that sort of stuff. Like that, I guess this is what I'm supposed to do sometimes, at least, right? Take on problematic notions and make them more complicated and show, how things change. And we also know what properties can hold in both the original space-time and nemesis, at least to some extent. But I think we have learned more about these notions than about black holes. It's sort of we have some of the black hole spacetimes are nemesis examples of the nemesis spacetimes. But it seems hard to kind of locate ourselves into many of them, right? Because we think of as Cray plus as a good idealization for many practical purposes, where we some of you actually said at some point, and Ramesh is quoted in print by Eric, saying that if we think of ourselves in the relationship to such a star, we're effectively a future non-infinity of that thing. And so in many of those examples, it's hard to locate ourselves inside, and so we can kind of represent us as observers inside those spacetimes, which I think should give us a pause if we think of this as a skeptical result. And also, like in situations like this, I didn't put any gravitational collapse, and that of course gives you like a timestamp and also again means of distinguishing these spacetimes. So I think we have learned a lot about these notions and nemesis spacetimes that we shouldn't make any kind of skeptical claims on black holes or singularities on the basis of those examples. That doesn't mean that better examples can be found, but at least those can be used for that purpose. Yeah, and I guess that's it. Thank you so much for preparing me.
Are you doing the questions? You want me to? Peter?
Sorry for going over time, but we had so much discussion during that always throws me off.
Should we stop for lunch? Yes,
We're only just on time, so we can take a few questions, I think.
so I just want to understand the broader programmatic aims of this. Is the goal to see what the definitional conditions of equivalence are, such that we can define the most realistic interpretation of space-time in some way? Is the goal to say just how far can we go and no farther? And so what I want to understand what the broad program
Mhm.
that helps us pick this out? Is it to say we have a hierarchy of strength of assumptions about what equivalents are? We want to sort of go down the list as far as we can, but no farther, such that space-time and its equivalent friends are well-defined and pick out a physical situation.
Uniquely or not,
Uniquely.
or maybe a kind of restrict. Yeah, it's close to unique, right? And it's just few of them as a space times and not a whole bunch of them.
Is
Yeah.
that the philosophical
That's
aim of the
that,
program?
that's I think a good way of thinking about this. Yes. Yeah, because then depending on what exactly those assumptions are, where in the kind of maybe not the hierarchy, but kind of like the network of relationship, they are, then some of those outlandish possibilities will be something that concerns me because they're kind of allowed by the sort of idealizations that I do employ or not. And some of the other ones would be something that would concern me if in a situation where those idealizations are not allowed, like in a SpongeBob situation, that do not have to concern me in a situation where some of those idealizations represented my epistemic situations are sort of like allowed. Yeah, I think that's one way to put it. But another thing for which, and it's sort of also useful for dual purpose because we learn more about kind of a conceptual dependencies within the field. So it's not that different from studying global hierarchy in a way.
Rush has a question.
Yeah, one of the examples, the one you note on the board, basically, I think was this and somebody,
Yes.
you say that you will take the singularity and do something to it, it's a different object, whatever. That looks really trivial to me in the sense.
Yes.
What you're saying is, if I restrict
Right.
myself to the exterior of the
Exactly.
horizon,
Yeah.
I cannot tell if somebody has changed the interior.
Yes. Yeah, I fully agree.
I mean, at that
Yeah.
point, it's come on, yeah.
Yeah, of course.
Yeah.
Yeah.
If you
Yeah.
allow your theory to have solutions that
Yeah.
look different in the
Yeah.
interior, you cannot tell on the outside.
Right.
Yeah. So
Yeah.
there it doesn't look very worrying.
For an astrophysicist. Yeah.
Actually, yeah. Okay, maybe philosophers worry too easily.
I worry all the time. Yeah. Yeah, no, but of course, if you're thinking of jumping in, right, that matters to you, whether it's one of these or solution or a Bardeen's solution or
Right, yeah.
yeah.
Okay.
But of course,
Okay,
yes.
Andy, you might worry about the correspondence between interior and.
Sure, all that is
Yeah.
fine, yeah.
Yes.
So, but you know, it's observationally indistinguishable, but that is
For you.
pretty
Yeah.
much the evidence, I mean, definition of the horizon. I
Right.
cannot observationally distinguish, you know,
Of
one
course,
version
yeah.
or another
Right.
of the interior.
Yeah.
Right,
I'm happy you said this because I should have said this, but
okay.
yeah.
Some of the others, I'm not sure whether I should worry or not. On the whole, I'm not worried, but.
Of course. Well, that's why I said you should
Should
look
I?
at this. You shouldn't be worried. Yeah, so some of these, I think, so out of the 5 black hole maybe I can put it like this. I had 5 black hole nemesis here. The first was the purely Wieser's one, so you have not to worry about. You don't have to worry about it. The second one, which we kind of like because it makes this weak POI relationship true. So it's kind of like this mixed version when I have a bit of the normal stuff and a bit of Wieser stuff. You also don't have to worry about this because it's in the interior. So I'm happy we have it because it's a nice example of something that's strongly COI in here, but also weakly OI generally, weakly POI generally. So it kind of like, you know, fits in the hole in the network, right? But you don't have to worry about it. This one where I do like kind of like standard cutting and pasting in the interior, you don't have to worry about as well, and glue it to the asymptotically flat thing. You don't have to worry about on the same grounds, right? And then there's this one, which I think is weird. I think it's a feature of the basically high symmetry of Schwarzschild and I guess Kerr, where we can do this kind of like take t equals constant and truncate it. And I think most people would say this is not physically reasonable because it's not as large as it could be. Why would nature stop constructing this space then? This is such an argument. And then there's a fun philosophical discussion that we could have about these sorts of principles. But like sort of, if you think of kind of like, oh, I'm traveling somewhere here and maybe I will hit this kind of like, kind of sudden kind of death of the world sort of situation. Okay, that can always happen, right? What do I care? And all of the, I kind of like lose the global stuff, but like all of this kind of smaller observations, they can all be made. But like, it's not a nemesis if I think of this as collapsing star anymore, because that gives me like a, right? Because that gives me kind of like a, so if I have this, that gives me sort of like a timestamp, right? That can distinguish the original one from the full thing.
I don't see that. You mentioned it in the talk, but
Okay,
what's
right.
wrong with this model with the collapsing stuff?
Without, right, so if, the way this works is that this is a weak, oh, it's actually a strong POI, sorry, this is my school, it's a strong POI, and that's rare. But not a strong COI. Anyways, that's the reason to sort of think about this. So it's a strong POI because no matter where I am in this one, I can always map myself into some sub-region of the truncated space-time. But if I think of this, oh, here's my star, it undergoes a collapse and it blows up. And so then if I'm kind of like here and here and here, it's a very different situation. But if I'm in the kind of like purely static black hole, that makes the difference, right? So this is what I meant, because like here I can equally well pick any T plus constant slice and remove and its future, but here it's not any longer the case, right? So this is what I meant.
Just the time translation,
Exactly.
symmetry is being lost.
Yeah. But here, if I work along the points, I can always push myself back, because as long as in stationary or static cases, which is why I think those examples are highly unusual. And again, I think as physicists, maybe you don't have to worry about them at all as well. And so the only remaining one is this one, where I do kind of like a complicated gluing, cutting and pasting. Yeah. Out of the 5 that we have found so far, maybe other people will find more, right? But that's I guess. So again, I think this ties nicely with what Peter pressed me about, sort of depending on what my epistemic goals are. Some of these examples will be worrying or not be worrying. I'm a reasonable person, stay outside. I don't have to worry about many of those. I will like, I had a bad day and I want to jump inside. That matters when I will be like, effective in that endeavor or not. Yeah.
In a sense, it starts to feel similar to a question of why you list the solutions given,
Yes.
the domain and boundary conditions that you have. In the sense that like if you, instead of considering like
Right.
your initial data to be all over Rn, you just consider it as a subset of Rn and
Yeah.
evolve it.
Yeah.
And then the question is that what sort of boundary conditions can you stitch onto that?
Yeah,
feels
yeah,
very similar to
You
this.
could think of this that way. Yeah. And so especially when people are do this thing where they worry that, where did I put all this on the slide?
Like if you do it in a 3+1 decomposition.
Yeah. When people do this thing where they worry about prediction, this is sort of like the situation they do. They think, oh, okay, maybe I'm in a space-time that has a Cauchy slice, but of course I don't typically have no access to the full Cauchy slice.
Yeah.
I have access to the partial slice, and then sort of like you do this kind of like stitching thing. Say, oh, you thought I could assume this is the boundary of domain of dependence. Assume I predicted something far up.
Yeah.
No way, I was unsuccessful because I could just as well be living in one of those stitched in space-time. So in a way, I think I guess it's not like a normal boundary condition given by a like nice equation, right? But I think it's spiritually similar to that. Yeah. But here the good news is that I didn't talk about that we do have a notion that maybe is a bit better than these. It allows you to recover some point prediction. Maybe not. But like, at least it's there's a promising other notion.
Okay, well, I think we should probably stop there and get to lunch, and I hope everybody will continue to
Yeah,
ask
yeah.
Juliusz lots of questions over that.
yeah, thank you. I'm really happy that will happen in another 2 months, in the next 2 months. But I guess we cannot know.